over 25 minus
yes.
3, so we get 6.
So we have the number of minutes, which is 60. Correct. Yes.
Yeah, so
awesome.
60 minus 50, which gives us 10.
Careful. Careful. It's multiplied. Don't rush. So you were correct here because it was. That's okay. That's okay. That's why we're here to learn. So you were correct here because it was plus. So times natural log of 15 over 25 minus t. Okay, good. So then the first step is to clean it up. We have to divide by 50. So we have 6/5 equals natural log of 15 over 25 minus t. Now we have to write the equivalent equation. How do I write the equivalent exponential equation?
I want to raise it by, I want to raise it to the e power. So e to the 6 over 5 power. That way I can get rid of the natural log. And have to do with 15 over 25t.
Good. Cross multiply now. And this is over 1. 1 times 15. E to 6/5 times 25 minus t. Yes, I will divide by this. And then what I would like to do, but you can multiply both sides by -1 at the end. So 15 over e to 6/5 minus 25 equals -t. And now we multiply both sides by -1. What does that equal to? No clue. So 25 minus 15 divided by e to power 6/5. 6 divided by 5. So I have 25 minus 15 divided by this, and I got 20.48. What does this represent?
Minutes per Celsius.
This is not the derivative. It doesn't have to have 2 measurement units. It's not the derivative.
Celsius. Oh.
That's it. So I think we have enough. This was an involving problem. It was, we had to be very careful on a lot of steps, right? A lot of steps, and the conveniency of changing this when I needed it into something easier. Plugging in, solving a logarithmic equation. It was interesting and not trivial, not a trivial problem at all. Any questions from me? Any questions? Any questions from Pearson? Any questions? Anything that you encountered? Anything? Is there anything you want to ask? Anything? Okay, so then we're going to start chapter 3, and I'm just looking to show you here. Chapter 3 is huge. Look at all this. This is chapter 3. From 264 to 366. 100 pages. A lot. So let's start. Chapter 3 deals with application. So in 1 and 2, we looked at derivatives. So in chapters 1 and 2, we looked at derivatives and limits, first of all limits, and then derivatives of all sorts of functions. Now in chapter 3, we are going to use what we learned in chapters 1 and 2 and do more applications. Now you can say, but wait a minute. What was this? Wasn't this an application of derivatives? Yes. What was this? Wasn't that an application of derivatives? Yes. So if you don't like the title, we're going to add to it more applications of differentiation. So we are adding the word more, just because. So we had a lot of applications. Every time we learn something, we look at anything that is new, we looked at applications. Now the entire chapter 3 has a lot of applications, more applications of differentiation. So one of the biggest applications here is graphing. And you can say, what are you talking about? We've been graphing functions like forever, right? From beginning algebra, we've been graphing functions. True. So how is this related to this now? You're going to see how. It's a long journey. It's not a very short journey. We're going to build on a lot of information. And you see what happens next. So first of all, first concept here is critical number. In your book is called value. It doesn't matter to me what you want to call it. Critical number or critical value. What is a critical number of a function? A critical number, so I'm going to abbreviate as CN, critical number of a function can come from two sources. Source number 1 and source number 2. Does a function have to have critical numbers? No. So I'm going to add here functions do not have to have critical numbers. They don't have to. You will see what happens if they do. If they don't, they don't. So a critical number of a function can come from two different sources. Here's one source. F prime of x is 0. So what does it mean? I have the function, I find its derivative, I set it equal to 0. If this equation has solutions, those are the critical numbers. If this equation has no solutions, then the function doesn't have critical numbers coming from this source. Again, critical numbers of a function can come from two sources. One source is, I have the function, I find the derivative, I set it equal to 0, and I find solutions, or solution. Those are the critical numbers. What is the second possibility? F prime of x is undefined at points or point where f of x is defined. That's a mouthful. What does it mean? And I want to give examples from both in a minute. What does this mean? The function has to be defined at a point where it has a critical number. So if the function is not defined at x equals 1, we don't care that f prime is undefined at x equals 1. That's not a critical number. So if f prime is undefined where the function exists, that is a critical number. So I'm going to give examples from each so you understand. Question first. Let's suppose we have this function. So this is our f of x. Is this function continuous everywhere? Anyone?
No, it is not.
Continuous. Continuous. Yes. Yes, it is continuous. Now I'm going to ask, of course, Sissy is ahead of me. That's awesome. Now I'm going to ask, is it differentiable everywhere?
No.
No, it's not differentiable here. Why?
Short.
Excellent. Excellent. This is this situation. The derivative does not exist. It's not differentiable. At this point, this is a critical number, so I'm going to call it C. C1. This is a critical number. The function, the derivative is undefined, but the function exists. So that is typical for part B. A corner, a vertical tangent, a cusp. The function is not differentiable, but it's continuous. And this point is a critical number coming from this source. F prime undefined because its function is not differentiable there, but the function exists. C1. Now, see at this point, let me use a different color right here. At this point, the slope of the tangent, which is the derivative. At this point, f prime of x is 0. This critical number, this value here, C2, is a critical number coming from this source, where f prime is 0. So from f prime is 0, we got critical number C2. And from f prime being undefined, we got critical number C1. Now, what's such a big deal about these critical numbers? Who really cares about critical numbers? Well, here's why we care about critical numbers. Note, only critical numbers may change or may turn into max-min. If a function does not have critical numbers, it will not have max-min. It cannot have a max, it cannot have a min if it doesn't have critical numbers. But there is a catch. If it has critical numbers, are they always max-min? No. If a function does not have critical numbers, it's carved in stone. It will not have max-min. If it has critical numbers, they may turn into max-min. No guarantee. There is an analysis that will follow to see if they turn into max-min or not. So here's another note. Critical numbers are followed by an analysis to find max-min. No guarantee. We can never say, oh, it has critical numbers. Guaranteed it has max-min. No. We will have to do an analysis for that. And then we'll conclude, oh yeah, it's a max. Oh no, it's nothing. Oh yes, it's a min. So that's why we are interested in critical numbers, because only critical numbers turn into max-min potentially. Okay. Now, I'm going to graph another function. And this is our function f of x. And maybe I should just stop for a second and look at, share my screen. And let's look at some graphs for a second. Which page am I on? I am on page 276. I'm sharing my screen. Let me go to 276 first. And enter. And then we'll come back to my graph. No, I don't want this yet. I'm going to come back to that. I want this for a second. So what do you think about x1? Is x1 a critical number?
No.
So let's take a look.
Oh, I mean, yes.
Yes, it is a critical number. Coming from which source?
It's a corner. Oh, negative infinity to infinity.
So let's. It's confusing. It's a lot of information all at once. So critical numbers can come from f prime being 0, or from f prime being undefined, where the function exists. This.
Okay.
This is from f prime being 0, and this is from f prime being undefined. So now I'm going to share my screen again.
So it's from f prime, f prime being undefined.
So let's see. Is it clear that this is this situation? Yes, it's this situation, but reversed. Right?
Okay.
Good. So this is from f prime of x equals 0. Now, what about this? Now, these graphs are a little bit confusing, but if you say that this is smooth, then this is nothing. If you want to say that right here there is kind of a corner, then I will say it's coming from undefined. It's a little bit confusing. But if you want to say that this is smooth, then I would say this is not a critical number. What about this one? Where does it come from? F prime of x being 0 or f prime of x being undefined?
F prime of x being 0.
Exactly. What about this one? And for this one, there is no ambiguity.
Undefined?
Yes. Because it's a cusp. And the derivative doesn't exist, but the function does. Awesome. What about x5?
I would say undefined because let's say there you have two different points coming in.
It's the same thing. It's the same thing as here. It's the same thing as here. It's not a cusp. It's not a corner.
Okay.
F prime being 0.
F prime being 0.
Good. Same thing here. Same thing here. Same thing here. What about 7? X7.
Undefined.
Undefined indeed. Finally, x9. So what they are trying to show here, to me, it looks like it's a vertical tangent. So if it is a vertical tangent, what type of critical number is this? Coming from which source?
Zero.
But 0 has to have a horizontal tangent.
Undefined?
Yes. Yes. So if it's a vertical tangent indeed, this comes from f prime being undefined, where the function exists. The function exists, but the derivative does not. Do we have an idea now about these critical numbers? Do we feel a little bit better about critical numbers?